Learning how to balance a chemical equation takes a little, a little practice. It's kind of an art. I can't give you a hard and fast rule, do this. I can just tell you what the end product needs to look like, and some techniques. We can do a few, and you can get an idea of how you get there. All right, we looked at this, just some different moles of things. We must, here's where I introduced the chemical equation. Here's some slides. So let's just kind of go through the slides that are available that repeat some of what I said. Here's a simple equation. How would you make water? Well, you can make water from hydrogen and oxygen. And those of you that were in the 1105 or had 1105 experiment this week, experiment 6, you actually did do this. When the zinc reacted with HCl and formed hydrogen, when you put a match up to it and went pop, what happened? The hydrogen converted into water. H2O plus oxygen, it will do that pretty explosively. As a matter of fact, there are some taxi companies right now running around with hydrogen-powered cars in cities where pollution is a real problem. They're trying to push this compressed hydrogen. You run around not with gas in your gas tank, you run around with a tank full of hydrogen. And you pump in hydrogen into your carburetor and air into your carburetor, and it's exploding. And what's it forming? Water. So the only thing that comes out of the back of the car is steam. Pretty neat, huh? Pretty neat. So if you're in a city that's really polluted and you could get 20% of your vehicles to be running around in cars powered by hydrogen, you can start knocking down that pollution. So there's a chemical reaction. There's the subscripts. Gas, liquid. Hydrogen is H2. It's a diatomic molecule. As an element, it exists as a diatomic molecule. Oxygen exists diatomically. Water is H2O. So you can't just say, oh, what's coming out of here is H2O2 because I got two oxygens over here. What comes out of this reaction is water. It's H2O. You can't change the formula just to balance the equation. That's where you have to go to coefficients. 2 times 2, I've got 4 hydrogens here. I've got 2 oxygens here. 2 times 2, I've got 4 hydrogens here. But I've got 2 water molecules, each one of them. 2 times 1, there's an understood 1 there, is 2. So it's balanced. What's balanced mean? Exactly the same number of every element on both sides of the equation. Balanced. It's obeying the law of conservation of mass. A chemical reaction does not create nor destroy matter. There's no creation or destruction of matter. Every gram of reactant comes out of the reaction. Not in the same form. It's not in the same form. Here it is water. Here it is 2 gases. Here's another example. This is a decomposition reaction. Here's mercury 2 oxide, HgO. How do you know that's mercury 2? Because you know oxygen is -2. And if you see a formula, HgO, it's got the charges above it there, really tiny. Okay, you know that oxygen is a -2, so this mercury is a +2. That's immaterial. Just where did we get that formula? HgO. Heat, this is a decomposition reaction. How do we know that? Well, we only got one reactant right here. And it's creating 2 two things. Two new things are the products from one reactant. So this reactant is decomposing into its elements, mercury and oxygen. And you can see it up here, the mercury. Here's the mercury, liquid mercury. You would definitely want to be doing this in a hood because you'd have hot liquid mercury. Mercury's poisonous. And the oxygen would be coming off as a gas. It would be leaving as a gas, leaving behind your mercury, liquid mercury, and your oxygen would be going off as gas. That's a decomposition reaction. This is a composition reaction. You've got two elements forming a product. We'll talk about types of reactions. So this is just going over some of those features again. Products and reactants must be specified using the proper chemical symbols and proper chemical formulas would be probably the better way of putting that. You got to have you have to have the correct formulas for products and reactants. The reactants are written on the left side, the products are written on the right, and physical states are shown with these little subscript parentheses at the end. Yeah, and a little triangle like that usually means a source of energy, usually heat, could be electricity, but some major source of energy is needed to drive this reaction. We'll talk more about energy in chapter 7. And then coefficients. Coefficients are used to balance the equation after you have the right formulas. And we read it as 2 moles of mercury 2 oxide produces 2 moles of mercury and 1 mole of O2. Oxygen is O2, so 1 mole of it. And it's a balanced equation. We got 2 mercuries and 2 oxygens on both sides of that equation. Yeah, types of release of a gas is an indicator that you've seen a reaction, formation of a precipitate. Heat being evolved, that's not always a proof that a chemical reaction took place, but if you do see heat changes, whether something got colder or hotter, it would suggest that there may be a chemical change going on. You can get some of that just by dissolving something in water. It can change its temperature. Color changes. A new color forms. There must be something kind of new developing there if you got a color change, major color change. Okay, at an atomic level, here's a reaction, hydrochloric acid with calcium to form calcium chloride and hydrogen gas. In your 1105 experiment this week, that would be comparable to when you reacted zinc with hydrochloric acid. Matter of fact, you react hydrochloric acid with almost any metal, zinc, iron, nickel, copper, magnesium, calcium, potassium. You're going to form the chloride of that metal and release hydrogen gas. That's a pretty general reaction. This is why, the old water pipes in homes and things like that, this is why you put Drano down a drain and not acids down a drain. The acid will react with the pipe. The acid will clean everything out of the pipe, including the pipe. Okay? It'll start reacting with the pipe. You do that enough, you have holes in your pipe. So acids attack metals. Bases don't. Sodium hydroxide, which is Drano, you can put that down the drain. It's really strongly basic, but any pipes or anything in your system, any valves, aren't being attacked by the sodium hydroxide. But they will be attacked by strong acids like this. Okay, at an atomic level, here's an HCl molecule and a calcium atom. I'm saying, what's really happening at the atomic level? Incorrect, incorrect. Here's the correct one. Two HCl molecules react with one calcium atom to form a calcium chloride. That's the ratio in the ionic crystal, and one hydrogen molecule. Here's your hydrogen molecule. Here's your two chlorides. Here's your calcium. So that's what's happening at the molecular level. At the mole, on the mole basis, 2 moles of hydrogen gas, that would be 2 times Avogadro's number of these, would react with the Avogadro number of these to form the Avogadro number of these and those, and you'd have, it would equal out. So whether we do it at the molecular level or the mole level, so 2 moles of this reacts with 1 mole of that to produce 2 moles of, or 1 mole of this and 1 mole of that. It's balanced. 2 hydrogens, 2 chlorides, 1 calcium, balanced equation. It's good just going through how to balance the H2O plus H2 plus O2 to form water. Let's do some examples. All right, here is a double replacement reaction. What do we mean by that? The iron is going to replace the silver, and the silver is going to replace the iron. So you're going to get iron nitrate, you're going to get silver chloride. So that's what I mean by double replacement. Each one of those species is replacing the other one. Let me see here a second. Let me do this one first. This one I think is the top of your, let me have one of these. Everybody have one of these worksheets? They're right back here. Worksheet. This is the first one on the worksheet. You got nitrogen, hydrogen, ammonia. So ammonia is a compound made up of nitrogen and hydrogen. What is nitrogen and hydrogen? They are diatomic elements. So they exist as N2 and H2. I mean, it would be beautiful if you just, you could write this equation like this. It'd be easier to balance, wouldn't it? I just need 3 hydrogens. Boink, balanced. But that isn't the correct formulas for the reactants that are going into the reaction. So we're not going to take the easy way out. So you look at an equation like this and you see 2 nitrogens. Well, here's one simple way. You could do a little bit of accounting. It's like this. I've got 2 nitrogens over here. I only have 1 nitrogen over here. I've got 2 hydrogens over here, and I have 3 hydrogens over here. Okay, the hardest thing to get even is going to be the hydrogens. So what is a common number of hydrogens that I can have? 6 hydrogens. So for example, if I multiplied this by 3, I would have 6. And I would need to multiply this by 2 to have 6. Well, what does that mean, multiplying it by 3? Having 3 H2s. 3 times 2 is 6. And what does that mean to multiply that by 2? I need a coefficient right here, 2. 2 times 3 is 6. So now I've got my hydrogens even. And notice that 2 NH3s is 2 nitrogens. So when you get to this point where everything is even, you're balanced. So the coefficient on the N2 is a 1. You don't need to write it. We don't write 1s. 1s are understood. So N2 plus 3 H2s is going to yield 2 NH3s. And that's balanced. And what that's really saying is that 1 mole of this reacts with 3 moles of hydrogen to produce 2 moles of ammonia. That's what that reaction is all about. I'll come back to that other one in a minute here. Okay, let's do it right now. Let's look at this one. And let me just tell you a few little tricks. You have already learned that that is a polyatomic ion. You have learned that that is a polyatomic ion. That is a polyatomic ion. That is a polyatomic ion. So what do I want to tell you about that? When one of these appears in a chemical reaction like this is the way I do it. You don't have to do it this way. You could break this down into silver, nitrogen, oxygen, iron, and chlorine. You can have a list of 5 elements over here. But if I see a nitrate and a nitrate, and I can see that nitrate is staying as an entity in the reactants and the products. This doesn't work all the time, it works most of the time. I leave it as an entity right over here. And then I list, this is probably the way a bank accountant would do it. I'm not a bank accountant. But notice I make my list: silver, nitrate, iron, chloride. So I just walk along here and say, what are my elements, or what are the components of the reactants? These are the components. I draw that same list right here in the same order. Why? Because I want to make this comparison. I want to compare right across there to see when I got this thing balanced. I got one of these. I have 1 nitrate. I have 1 iron. I have 3 chlorides. You agree? That's what I have in the reactants. In the products, I have 1 silver. I have, how many nitrates do I have in the products? 3. And I have 1 iron and I have 1 chloride. So I got a couple 3s over here, but in the wrong place. I've got 3 chlorides, I only got 1. 1 nitrate, I've got 3 nitrates, okay? So, start somewhere. Start with either one of these 2. You got to do something to get this or this balanced. So one way we could get that balanced, we got 3 nitrates over here. How could we get 3 nitrates on this side? How? Put a 3 in front of the compound that contains the nitrate. And I get 3 nitrates. That gives me 3 silvers. So that knocks the silvers out of whack, but just hang on. Hang on. Story's not over. We're not into the last scene of the play yet. So we have our nitrates balanced. We now have 3 silvers. We only have 1 silver there. So how do I get the silvers balanced? Put a 3 in front of the silver. And what does that do to the chloride? 3. Is that good? Is it all balanced? Okay? So kind of stick with it. Do these in pencil. Why do them in pencil? You may start out with the wrong element. No, I'm not starting out with the wrong element. You may start somewhere and you kind of chase that down a trail and it doesn't get you anywhere. So erase it and try something else. We started here. We knew this. We had 3 of these coming out in the product, so we had to have 3 of them going into the reactants. So that's where we started. So, okay, I'm going to get my nitrates balanced. We could have started here. We could have said, okay, I've got 3 chlorides here, and I only have 1 chloride over there, so I'm going to put a 3 there to get the chloride. See, it would have still gotten me there. Would have still gotten me there. You got to start somewhere. Okay, let's look at this sheet. Let's do. Let me do a couple with you. Let's see. I don't have. Yeah, I do have a couple. So let's do number 2. I'll just do it down below here. This is going to be number 2. K. By the way, this is the 1105 experiment next week, the decomposition. Oh, I should have asked you, what kind of reaction is this? But can you see this is a decomposition reaction? And notice, decomposition doesn't mean that you produce 2 elements. You have one thing decomposing into 2 other things. In this case, it's decomposing into a compound, potassium chloride, and oxygen. Okay, take a stab at that. Make your little list of K, Cl, and O. I'll take that 2 off there. I didn't know that. I think that's a coefficient. You don't have 603s. You just have O. Just put O there.
Oh.
Okay? It just, how many O's do you have? You have, with the 2 times 3, you have 6. You have 6 O's. Okay?
Oh, okay.
You don't have 603s.
Okay.
603s would be 18 O's.
Yeah.
Got it? Not yet? Not quite. Yeah, so, okay. Good. Did you get it? Let's see what you got. Okay, good. What, you're barreling ahead, huh?
I'm trying to focus.
Okay, good. Did you get 2? Or what is it, 2? Yeah, all right, good. Good. Let's see. Did you fix it?
Yes.
No, you didn't.
Oh, no?
Look at your oxygen. Look at your O2. How many O's are there?
Oh, it's 3.
There you go, okay? There you go. All right?
Yeah.
All right? Check and double check.
Okay.
Make sure you got what you... Okay, I think most of you are getting this. You can see that oxygen is what you have to attack here. We've got 3 on the one side and 2 on the other side. Now you can't get that balanced unless just with fractions. We wouldn't want to do it with fractions, so we want a whole number. So 2 times 3 is 6 oxygens, and 3 times 2 is 6 oxygens. All right, so you start with your oxygen on this one, and then you follow the implications of that. This is going to get you 2 potassiums and 2 chlorides. So we're going to need a 2 right here to get the 2 potassiums. And what does that give you? 2 chlorides. If you absolutely cannot balance a chemical equation, it's probably not a correct chemical reaction. Has to balance. Has to balance. Why? Because the law of conservation of mass. If it won't balance, then something's wrong. I've had that. I've handed out sheets, and Mr. Riak, we cannot balance this equation. And I look it up and I go, oh, I got the wrong product coming out of there. You can't make that with that reaction. It has to balance. There has to be some way to balance it. With integers, we're going to do this with integers in front of everything. Those coefficients are all going to be whole numbers, but they can be big whole numbers. We'll get a couple examples of that. So that was number 2. All right, let's look at number 7. If you look at 7, 8, and 9, those are the kinds of things that we burn. 7 is natural gas. We burn it in our furnaces. 8 is propane. We burn it in our grills. And 9 is octane. We burn it in our automobiles and vehicles. That's the main component of gasoline. And look at the similarity there. It's a compound, a hydrocarbon, carbon-hydrogen compound, plus oxygen, yields carbon dioxide and water. The other reactant is always oxygen, and the other products are always carbon dioxide and water. There is a little variation on that, but let me tell you I want to show you how to address those kinds of reactions. Here's some examples. Here's the propane. Here is butane. You see? Propane plus oxygen, carbon dioxide, and water. Now, let's take the methane, the simplest one, as a start. Now this is complete combustion. Of hydrocarbons. Complete combustion. We're burning them down to carbon dioxide and water. All right, so we have carbon. This is the choo-choo method. All right? Carbon, hydrogen, oxygen. Carbon, hydrogen, oxygen. Think of it, choo-choo method. Why? Because this is the order in which to attack these kinds of balancings. Balance your carbon, then balance your hydrogen, and then finish off your oxygen. Your oxygen is sitting over here all by itself, so it can be fiddled with well at the end if you get this right. So what does this mean? How many carbons am I starting with in the reactants? How many hydrogens? How many oxygens? Okay. So 1 carbon, I need a 1. I don't need to write a 1, but that 1 CO2 gives me 1 carbon. 4 hydrogens. So what do I need in front of the water to balance the hydrogen? 2. I need a 2 here. 2 times 2 gives me 4. All right, now come on over here. I've got these right. I've got oxygen in both of those products. So figure out how many oxygens. You have 2 oxygens coming from the carbon dioxide and 2 oxygens. 2 times 1, don't forget this, 2 times 1 is 2 oxygens coming in, which is 4 oxygens. So what do I need to do over here? Put in a 2. 2 times 2 is 4 oxygens. Okay. All right, so try the choo-choo method on propane. Look at the rest of the reaction is the same. Is that the next one? Is that number 8? Yeah, number 8 is propane. So try that. Carbon first, hydrogen second, and then clean up the oxygen. We got it? Got it? You got it. Oh, you got that one too?
Yeah.
Okay. I think that's right. Okay, now notice here, every one of these can be divided by 2. Every one of those numbers. So do that.
Oh,
Divide
okay.
every number by 2. Okay? That would be a more accurate number. We want it down into the reduced form. Okay. All right. I look here. I've got 3 carbons, so I need a 3 right here. I've got 8 hydrogens, so I need a 4 right here, right? Four times 2 is 8. And now how many oxygens? 3 times 2 is 6 plus 4 is 10 oxygens. And so I just need a 5 right here. And it's balanced. Okay, let's do one with a little twist to it, just one more with a little twist. C4H10 plus oxygen. One with a little twist. Do it the same way. Approach it the same way. This is butane, so little butane lighters. I think they still sell them. Is that right? Do they still sell little butane lighters in gas stations and things? People used to use a little butane lighter to light their cigarettes. The little lighter with a little liquid in there, that was butane. spark at the top, and they've got a little flame instantly. Okay, what's the little twist here? How's your oxygen coming up? Odd number or even number? Odd number of oxygens. And oxygens come in pairs. Is that are you there? Are you struggling with that problem? I got 4 carbons, so 4 CO2s. I've got 10 hydrogens in CH4 or C4H10. So I need 5 water molecules. That gives me 10 hydrogens. But now I get 8 oxygens from the CO2 and 5 oxygens from the water, which is 13 oxygens. So what is 13 oxygens? It is 6 1/2 O2 molecules, right? 6 O2 molecules is 12. 7 is 14. So we're right between 6 and 7 oxygen molecules, 6 1/2. Okay, now what can we do about that? We don't like fractions. We don't like to say, oh, 1 mole of that reacts with 6 1/2 moles of that to form 4 moles of that. And it's correct, that's balanced, but we would like to elevate that up to an integer. If you were making pancakes and you got oil and milk and what do you got? Oil, milk, flour, what else? Sugar? Eggs. Forgot the eggs. Got to have some eggs in your pancakes, right? Eggs, oil, milk, and flour. There you are. And it makes 12 pancakes. You go, I need 24 pancakes. Do you just double the eggs? No, when you double a recipe, you double everything in the recipe, right? See, everybody knows that. They're shaking their head. They're cooks. All right? So we got to double this recipe. We don't just double that, multiply that by 2, and we got 13. We can't just leave it there. We got to multiply that by 2, that by 2, and that by 2. We got to double this reaction. So whatever the coefficient was times 2. 2 times 1 is 2. 2 times 6 1/2 is 13. 2 times 4 is 8. And 2 times 5 is 10. That's the only 2 cases you're going to have with these combustion ones. You're going to either come out with an even number of oxygens over here and be able to quickly just get that number of oxygens by multiplying by a number over here, or an odd number of oxygens where you end up with a fraction, and then you'll need to double it. We won't do it right now, but number 9 is like that. I'll leave that. Matter of fact, I'm going to leave the rest of these for you to do. And if you come back on Tuesday, I've got the answers to all of these. So you work these out, and I'll hand out the answers on Tuesday. All right, I want to move on now to mass calculations. Some of these get a little bit more difficult. There's lots of different things in there. Yeah, so just work with them. This is 21. It gives you some practice, and then that other sheet that I gave you on Tuesday is a few more reactions. The best way to learn how to balance accurately is just practice. There's some more slides here. We just did this one. This one is one that would be kind of interesting and a bit challenging. Why? Because our hydrocarbon, this is an alcohol. This is ethanol. We're burning ethanol, and so we've got oxygen. We've got oxygen in everything. So that one's a little bit more, takes a little more gray matter to do that one. So they're on the slides. Okay, calculations. let's go back to my favorite reaction, and because this is what we were here making aluminum. I don't know if it's my favorite reaction, but it's one that I pick on a lot. And we balanced it. Do you remember the way we balanced it? We put a 2 here, we put a 3 here, put a 4 here, and that had us with a 3 here. Got a bunch of different coefficients. And the extent to which we had gone, I wish there was a way for me to copy that easily. We got to this point where we said, you know, this is reading 2 moles of this reacts with 3 moles of this to form 4 moles of this and 3 moles of this. And we did a simple little problem, fairly simple little problem. I forget the exact number, but we said, for example, this says here that you get 4 moles of aluminum for every 2 moles of aluminum oxide that reacts. Okay, where am I getting that? I'm just these coefficients are telling me that's the relationship between the moles of aluminum that are going to be produced and the moles of aluminum that reacted. And we did a problem. I think I said, I forget the number, but I said, how many moles of aluminum can be made from, let's just pick a number, 6.95 moles of aluminum oxide. Remember that? Problem like that? 6.95 moles of aluminum oxide equals how many moles of aluminum? So I want to convert moles of aluminum oxide into moles of aluminum. So I want to put moles of aluminum oxide down here. 2 for every 4 moles of aluminum. All right, by putting it in this order, moles of aluminum per mole of aluminum oxide, I convert moles of aluminum oxide into moles of aluminum. Okay, I'm gonna kind of label these problems. This is type 1, mole to mole. We're going to do 3 major types here, okay? So we have 6.95 times 4 divided by 2, and that's going to be 13.9 moles of aluminum. I talk about continuous improvement or ongoing learning. So my next thing to learn is how to take a screenshot of that reaction right there and copy it onto a new slide. Because I want to go on to type 2 problem. I want to use the same exact example. So I don't know, maybe by Tuesday I'll know that. We're not going to figure it out right now. Okay, you with that? Follow this, because the type 3, the third type of problem is going to be the one you're going to do the most. You're going to do it over and over again. But I want to walk us there so you see what I'm doing. So that's type 1. And you could do this problem. You could have this kind of problem for anything. I mean, I could ask the question, how many moles of carbon dioxide would be produced if 6.95 moles of aluminum oxide? We won't do the calculation, but if I had same thing, if I reacted 6.95 moles of aluminum oxide, and I wanted to know how many moles of CO2 resulted. Now you tell me what this should look like right here. What should that look like? I want to convert moles of aluminum oxide into moles of CO2. This is still this type of problem. We're going from moles of anything to moles of anything else in this chemical reaction. What should be up here? 3 moles of CO2. We want to get to moles of CO2 per what? Per 2 moles of aluminum oxide. Okay? Now let's yeah. And it doesn't always have to be a reactant going to a product. That's what these two are. But I got a situation where I've done this reaction and I've discovered that 4.5 moles of CO2 came out of the reaction. So let's say we had this situation where 4.5 moles of CO2 were produced. I got a gas, I analyzed it, weighed it, whatever, and I found there were 4.5 moles, but I wanted to know how many moles of aluminum oxide would have had to react to produce that. So I've got a product, and I want to find moles of a reactant. All right, so yeah, you can still see everything. Let me just move this down just a little bit. So now I want to relate moles of CO2. I want to convert moles of CO2 into moles of aluminum oxide. So now what does this need to look like? Okay, and that is correct. The way you kind of get that is I want to get rid of this, so this has to be down here. So this that has to be down there is you get 3 moles of CO2, not CO3, CO2. The relationship is 2 moles of Al2O3 per 3 moles of CO2. So you can set these relationships up either way. Here we got CO2 in the numerator and Al2 in the denominator. Why? Because we wanted to convert moles of Al2O3 into moles of CO2. Now here we got it reversed. That is the relationship. Just make sure you drag along the correct coefficient. Okay? You know moles, what is this? It's 2 moles of Al2O3 for every 3 moles of CO2. And this crosses out, and it leaves the unit. There's an equal sign right there. So what does that mean? Everything on this side of the equation has to equal what's on that side of the equation, including the units. The units have to be the same on both sides of that equation. And they are. Okay, type 2. I'm just kind of naming these like this, but we're going to go from moles to grams. This is going to be a mass calculation. Let me write our equation again. And let's say here's here's a type of how many grams of aluminum can be produced from 3.55 moles of aluminum oxide. Okay, I'm going from moles of aluminum oxide, and I want to calculate the grams of aluminum. That's what I want to calculate. So start over here, here's the roadmap. The roadmap is here. We're going to go from moles of aluminum oxide. We're going to convert that to moles of aluminum. And we're going to convert that to grams of aluminum. So this is going to be a two-step, well, we're going to put it all in one equation here. But there's two steps to get to the the goal line here. So here's where we're starting. We're starting back here on our 10th yard line. Well, actually, we're starting here on our 45th yard line. We only got 55 yards to go for a touchdown. And we want to know this. And that is an equal sign back there. All right, so the very first step is the type 1 problem. It's a simple type 1 problem. Just what we've just learned. So we need to convert moles of aluminum oxide into moles of aluminum. So it's 4 moles of aluminum per 2 moles of aluminum oxide. And can you see right now, we're right there. We don't know that number. We don't know that number yet. We'd have to pull out our calculator and calculate it, but you don't need to do that. Don't even pick up your calculator yet. But you've made progress to here. Okay, so how do we progress from here to here? How do we go from moles to grams? This is a skill you've learned. Grams over moles, right? So we need a unit like this, grams per mole. What is that? That's the molar mass. Grams of aluminum per mole of aluminum. That's the molar mass of aluminum. And where do you get that? Periodic table. What is it? 26.98. 26.98 grams of aluminum per mole of aluminum. Per mole, that means per 1 mole. If you say my car gets 26 miles per gallon, what are you saying? Per 1 gallon. 1 gallon of gas, I go 26 miles. Per anything, when you say per anything, I got 32 pounds per square inch of pressure in my tires. Yesterday I didn't. You know, I mean, got those little lights that come on that say your pressure's down. I got a car now that has pressure lights on it. And it showed up and, gotta go get air. All right, so per anything, it's per one of those things. So this is the molar mass of aluminum. It's the mass in grams of 1 mole of aluminum. And now, moles of aluminum cross out. And what do we have here? We got grams of aluminum, bingo, time to pick up your calculator. When you get the units right, it's time to pick up your calculator. 3.55. Wow. Now, rounding that off to 3 significant figures. I gave you the moles of aluminum oxide in 3 significant figures. This is a perfect relationship. There's not one significant figure right here. Exactly 4 moles of aluminum are produced from 2 moles of aluminum oxide. Exactly. It's a law of conservation of mass right there. Those are exact numbers. That's an exact number, 26.98 per 1, not per a half or whatever. So you get a number like 192, rounding it off to 192. Okay. All right, we have time for a type 3 calculation. And I'll stick with aluminum oxide and aluminum. Maybe I'll do a little bit of a twist here. Yeah, I think I'll do just a tiny little twist. So what you needed to know to solve this problem is you needed to know this molar mass. You needed to know the molar mass of aluminum. Got it off the periodic table. Let's go on to a type 3 problem. Stick with me. This is the most important one. We'll probably only have time to do one right now. We're going to go from grams to grams. This is stoichiometry. This is straight stoichiometry. Because I can't go in the lab and weigh out 4 moles of aluminum oxide or 3.55 moles of aluminum oxide. If I want to do a reaction, I have to weigh out my aluminum oxide in grams. And I'm going to get something at the end and weigh it and see how much aluminum I got in grams. So reactions in laboratories in Alcoa, reactions are mass to mass. They're taking certain tons of aluminum oxide and making so many tons of aluminum. They're going from mass to mass, not moles. But they need moles to do it. Okay, now while I rewrite this equation here, figure out the molar mass of aluminum oxide. All right? Figure out that molar mass. What is the molar mass of aluminum oxide? What is this number? Is that right? Okay. So what do we get here? 11. Is that right? Okay. This is what you need to do. You'll need to do this in these mass calculations. Now, aluminum was simple because we got it right off of because it's an element. It's coming out as an element. But this is a compound, so we have to figure out its molar mass. 101.96 grams per mole. Okay, now let me trip this up a little bit, because if we were at Alcoa, if you're in marketing or you're the CEO of Alcoa, you don't tell manufacturing how much aluminum oxide to react this month. You tell them how much aluminum you want. Okay? You tell manufacturing, here's how much aluminum we're going to sell next month. This is how much I want you to make. They have to figure out how much aluminum oxide to order and react. You follow me? This is their product. Sales and marketing and the CEO in the corner office, he knows how much of that they're hoping to sell. So that's the order that comes down to manufacturing. Make that amount. So here's going to be our question. How many grams of aluminum oxide would need to react to produce 29.3 grams of aluminum. Now, Alcoa wouldn't work in grams, they'd work in tons or metric tons or something like that. So, but we're going to stick in grams. We're going to go from grams to grams. All right, so let's move this up right there. We've got our molar masses. Here's the road map. We're going to go from grams of aluminum. We're going to convert that into moles of aluminum. But why am I starting with grams of aluminum? Starting from grams of aluminum because that's what I'm given. That's what I'm given. I want to produce 29.3 grams of aluminum. How much aluminum oxide needs to go into this reaction? So grams of aluminum to moles of aluminum to moles of aluminum oxide to grams of aluminum oxide. Okay? So this is 4 little steps here. All right, so let's see where we are started here. Right now, we got 29.3 grams of aluminum. And we want to come over here and get grams of aluminum oxide. Now we are back on our 10-yard line. We're on our 10-yard line, and we want to make a touchdown. Okay, this is a little harder problem than type 2. So if I have grams of aluminum, how do I convert that into moles of aluminum? What needs to go down here? Grams of aluminum. And what has to go up there is moles. And so we have 1 mole of aluminum per 26.98 grams. It's still the molar mass, but the inverse of that. We're putting the molar mass, 26.98 grams, in the denominator. So now I have moles of aluminum. Now how do I convert from moles of aluminum to moles of aluminum oxide? A requirement for this is a balanced chemical equation. Equation has to be balanced. Can't do these calculations without first correctly balancing the equation. So we're going to put moles of aluminum down here and moles of aluminum oxide up here. And those numbers are two of these for every 4 of these. That crosses out moles of aluminum. That moves us over to here. Okay, so we're here. We're now on the 20-yard line. It's close to the goal. And I need to put something like a mole of aluminum oxide down here and gram of aluminum oxide up here. I need to multiply by grams per mole, and in this case it's 101.96 grams of aluminum oxide per mole of aluminum oxide. Moles of aluminum oxide cross out. And let's do this. 29.3 times 2 times what do you get? 3 significant figures. 55.4. All right. Okay, we'll have to do another one like this on Tuesday. Let me just point one other thing out here real quickly. notice I don't just put 1 mole per 26.98 grams. I'm labeling this in here. What am I talking about? Here I'm talking about moles of aluminum. Because now I'm going to start talking about moles of aluminum oxide. You got to be careful here. If you don't label these correctly, a mole will cross out a mole, but you may be crossing out bananas from oranges. You follow me? You got to make sure it's moles of apples crossing out moles of apples. So that's why I label these things. Folks, here is 2 sign-up sheets, Monday and Tuesday, October 23rd, October 24th, to man our little table out here, giving away water bottles. I've got 2 people for 10, 10:30, 11, 11:30, 12, 12:31, 1:30. It would be ideal if 2 of you would say, oh, hey, let's both go at 10 o'clock, or let's go at 1 o'clock, or 1:30. Why? Because if you show up and you're all alone, you might have someone you can call. Where are you? All right? So why don't you team up, and if you can. If you can't find a team, then just put your name in there, and someone else will put their name in there. I'll put these back here. And let me tell you one other thing. I've got a list of tasks. If you couldn't come on Saturday and help, I've got some tasks here that it says here, tasks to prepare for mold day done during any of my office hours next week. What are some of the tasks? Labeling the water. We got to label about 120 bottles of water. Putting together those questions for people to pick out questions. Putting some signs together. What is pH and how do you measure pH? If you come during my office hours, I'll give you a little task to do. If you want to volunteer, whether you sign up to volunteer or not, come during my office hours and I'll say, yeah, here's something you could do to help for the mold day, all right? So take a look at those as you're leaving. And let me just get the attendance real quickly here. Saria, Taylor,
Here.
Veronica,
Here.
Samantha, Maria,
Here.
Carlos,
Here.
Julia.
Here.
Yeah. Let's see, which one? They're back there. They're back. Here they are. They're different kinds. Julia, Lindsay, Shayla, Christian, Laween, Jasmine, Trang, Tiffany, Jonathan, Sandra, Monica, Danielle, Matthew, Gabriel, Sam, Catherine, Brianna, Tori, and Vo. Okay. In the lab?
It's not the lady, it's not
Lena?
Lena?
Is that her name? Lena Rafati. Yeah?
Oh, yeah, I know.
Lena Rafati. Is that who it was?
Is that that girl?
Yeah, the
I'm
3
not
of you
sure.
were working
Yeah.
together? Yeah, I think so. I think that's who it was.
I thought she kept my slides, the lecture slides, so I can ask her if she
Okay.
had it. Thank you so much.
Okay.
Sure. We have to do a lab, right? What if we didn't go to the water lab? We can't volunteer. 'Cause I couldn't make it. I had work.
You mean Friday?
Yeah,
What-
that last week. Yeah, Friday from 9 to 11.
No, you can work there. You didn't have to come to the lab. No.
Oh, I could still volunteer at a
Yeah.
Are both days 2 different things?
Yeah, they're 2 different days, Monday and Tuesday.
So are they 2 different things that we have to do?
Like,
No.
are they 2 different extra credits, or is it just one? Like
Just
either one?
Either one.
Okay.
Either one. So I need 8 people. Well, what do I need? I need 8 people each day, don't I? I think I need 8 people each day. So, so yeah, just once. Just volunteer once. Unless I only get 8 people, I may say, hey, can you pick another time?